The radiation damage process illustrates why this threat differs fundamentally from gravity-related challenges. When radiation particles strike DNA molecules, they can cause breaks in DNA strands and loss of DNA bases. If the cell's repair mechanisms fail or make errors during repair, mutations become permanent. Unlike muscle or bone, which can rebuild with proper stimulation, damaged DNA represents a one-way deterioration process. Each mutation slightly increases cancer risk, creating a statistical inevitability of cellular malfunction given sufficient time and exposure. Radiation presents unique challenges for Mars habitation because humans cannot develop natural resistance to it. Evolution has never equipped us with cellular mechanisms to resist space radiation, as Earth's magnetic field and atmosphere have shielded life throughout evolutionary history. Unlike cold adaptation or altitude acclimation, radiation resistance cannot be developed through exposure. Quite the opposite, as exposure only increases cumulative damage. NASA's Human Research Program recognizes radiation as one of the most significant barriers to Mars exploration. Their research focuses on developing countermeasures across multiple fronts. These include shielding materials for vehicles and habitats, pharmaceutical interventions that might offer limited radio protection, and propulsion technologies to reduce transit time between planets. The practical implications for Mars settlers prove daunting. Surface activities would require strict time limitations. Habitat designs would require massive shielding or underground construction, dramatically increasing mission complexity and cost. Even with optimal protective measures, cancer risk would remain significantly elevated, creating ethical questions about acceptable risk thresholds. What makes radiation particularly insidious is its invisibility coupled with delayed effects. Unlike the immediate sensations of low gravity or extreme temperature, radiation damage accumulates silently, potentially manifesting as cancer decades after exposure began. Mars settlers would live with the knowledge that their DNA sustains daily damage that could eventually prove fatal, while never being able to sense the threat directly. The radiation reality forces us to confront an uncomfortable question. Can human biology, fundamentally adapted to Earth's protective environment, ever truly thrive on a planet bathed in cosmic radiation? The answer requires sophisticated protection strategies shielding the human body. The sophisticated protection strategies we're developing for Mars settlers reveal an uncomfortable truth. The difference between a spacecraft's aluminum shield and what humans truly need on the red planet resembles comparing a paper umbrella to a concrete bunker during a cosmic hurricane. As we'll see, the engineering challenges of protecting human life against particles moving at nearly the speed of light forces us to reimagine what Mars habitation might actually look like. Current spacecraft shielding technology faces a fundamental limitation against Mars' radiation environment. Standard aluminum hulls can deflect some radiation, but they're virtually transparent to high-energy galactic cosmic rays. These heavy ions travel at nearly the speed of light, penetrating spacecraft materials and human tissue with devastating efficiency. The physics problem is straightforward, but nearly impossible to solve. How do you stop particles moving at relativistic speeds without creating shields so massive they become impractical to transport to Mars? The limitations of traditional shielding become more apparent when considering the practicalities of Mars missions. Every kilogram of shielding material requires fuel for transport, creating a compounding problem. Engineers must balance protection against launch costs and payload constraints. This balance typically results in compromises that leave crews vulnerable to radiation exposure over extended Mars missions. While spacecraft can incorporate strategic shielding around sleeping quarters and high-occupancy areas, complete protection using conventional materials remains elusive. Fortunately, several promising materials offer potential solutions to this radiation challenge. Water serves dual purposes in spacecraft and habitat design. Its hydrogen content makes it remarkably effective at absorbing radiation, particularly neutrons produced when cosmic rays interact with spacecraft materials. Future habitat designs could incorporate water tanks strategically positioned to shield living quarters. A water barrier 40 centimeters thick can significantly reduce radiation exposure, while simultaneously providing a critical resource for the settlement. Martian regolith, the loose soil and rocky material covering the planet's surface, offers an even more promising local resource for radiation protection. Unlike water, it doesn't need to be transported from Earth. Studies suggest that approximately 3 meters of packed Martian soil would provide radiation protection comparable to Earth's atmosphere. Habitat designs could incorporate regolith-filled walls or be covered entirely with soil gathered and moved by autonomous robots before human arrival. This dirt shield approach represents one of the most practical near-term solutions for surface habitation. Despite these material solutions, significant challenges remain. The process of collecting and using regolith requires energy and machinery. The fine, abrasive nature of Martian dust presents contamination challenges. Additionally, habitats designed to support the weight of 3-meter soil shields require substantially stronger structural elements, increasing construction complexity. Underground habitats offer perhaps the most effective radiation protection strategy, taking advantage of natural shielding provided by Mars itself. By establishing settlements within caves, lava tubes, or excavated tunnels, settlers gain the equivalent of unlimited regolith protection without the construction challenges of surface buildings. Radar investigations have already identified potential lava tubes on Mars that could house entire communities protected from radiation and other surface hazards. The underground approach fundamentally changes our vision of Mars settlement from the typical science fiction depiction of geodesic domes on the surface to something resembling ant colonies with limited surface exposure. While practical from a radiation perspective, this underground existence creates profound psychological and operational challenges. Humans evolved under open skies, and extended subsurface living could trigger claustrophobia, disrupted circadian rhythms, and other psychological strains. For necessary surface activities, specialized spacesuits with enhanced radiation protection will be essential. Current spacesuit technology offers minimal radiation shielding, designed primarily for shorter duration activities. Mars explorers would need next-generation suits incorporating hydrogenated materials and potentially active radiation detection systems that could alert wearers to increasing exposure levels. However, truly effective radiation shielding adds weight, limiting mobility and extending already complex surface operations. The challenge extends beyond materials science into biology and medicine. Researchers are investigating radioprotectants, compounds that can shield cells from radiation damage or accelerate repair mechanisms. These range from antioxidants that neutralize radiation-generated free radicals to more sophisticated agents that enhance DNA repair mechanisms. Some compounds show promise in laboratory settings, potentially reducing radiation damage by 30 to 40% when administered before exposure. Biological interventions face significant hurdles before implementation on Mars missions. Most radioprotectant compounds require administration shortly before radiation exposure, making them impractical for continuous exposure scenarios. Others show concerning side effects during long-term use. The most promising approaches combine multiple protection strategies, physical shielding, habitat design, and biological interventions to create defense in depth against the radiation threat. When we assess these protection strategies, a sobering reality emerges. The most effective approach will likely involve establishing primarily subterranean habitats with heavily shielded transportation systems between them. Surface activities would be strictly limited to essential operations, conducted by personnel tracked for cumulative exposure and rotated to minimize individual risk. This radiation reality raises profound questions about Mars settlement itself. If humans must spend the majority of their time underground to avoid dangerous radiation exposure, can we truly claim to be living on Mars rather than merely living in Mars? The distinction matters both philosophically and practically for mission planning and settler psychology. The vision of expansive Martian vistas and surface exploration that motivates many Mars enthusiasts may be limited to brief, carefully managed excursions from underground havens.